So we covered cross-correlation, and we covered multiplication. And so those problems seem to really lend themselves very naturally to the proof technique that we chose, right, this information transfer technique. So one might wonder, well, one ought to wonder, well, what about other problems, right? There's no particular reason why in the same streaming setting, other kind of pattern matching type problems. And it turns out that as soon as you veer away from multiplication, things get more difficult in interesting ways. So the next problem we looked at was that of computing the Hamming distance, exactly the same setup but the Hamming distance. Now I should explain that the Hamming distance proof technique, which I will give a very brief overview of, is rather beautiful and rather sophisticated, and it will be explained in great detail by my colleague Ben Satch on Friday, and I highly recommend going to it because it's a wonderful thing, but it's much too much to describe as part of a 3-hour tutorial. So I'll just try and give a brief overview of essentially what the problem is, why is it hard, and very vaguely what do we do to solve it. So you remember again, we have some fixed string, call it a string now because we're computing Hamming distance, and every time a new symbol comes into the stream, we want to output the Hamming distance between our string s and the n-length suffix of our stream. And we're going to show the same lower bound we had before, delta over w times log n. Delta is the number of bits needed to represent a symbol, w is the word size, and n is the length of our string. So it's the same lower bound, same upper bound applies by the same reduction we had before, so it's going to be tight again. But what's the problem? Well, why don't we just try the same hard pattern we had before? Well, remember this pattern we had before. We had ones at power of 2 positions starting from the right. The difficulty we have here is that when we have a 1 aligned with something in the unknown region, all we get to find out is whether the 1 equals that symbol or doesn't equal the symbol. Whereas previously, in the inner product case, we actually find out what the symbol was. Now we just get one bit of information. Does it equal it or not? And the alphabet size is large. That doesn't tell you a whole lot about the symbol, right? Whether it just equals 1 or not. In fact, you could imagine maybe it never equals 1, depending on what the input distribution is. So this just doesn't give us much information. So let's try and summarize the reasons why Hamming distance is more difficult than convolution. The Hamming distance between two symbols just tells you whether they match or not. It doesn't tell you anything else about the symbol. Whereas multiplication tells you a whole lot about the symbol. If the alphabet size is large, this is going to be some random input distribution in the stream, right? If alphabet size is large, then the Hamming distance is going to be very large. Basically, everything's going to mismatch. But if the Hamming distance is always very large, then the entropy of outputs is going to be very low, right? If the answer, for example, is always n, then the entropy of output is extremely low. But if it's either n or n minus 1, then it's going to be small. But if the output size is small, then by our definition of conditional entropy of these outputs, the entropy can't be any larger than the entropy of the input. And so if the alphabet size is small, the entropy of the input is going to be small. So that's also bad. And it's also not at all clear what this worst case fixed string should be. So we have a problem here. We have a problem that Hamming distance just doesn't tell you much about a symbol. We don't want to have large alphabets, we don't have small alphabets, and we don't know what a worst case pattern should be. I just want to kind of convince you it's highly unobvious what you should do in the Hamming distance case. It's just much more difficult than the cross-correlation case. Okay? I can see some nods for difficulty. So this, in broad brush, is what we did. So rather than having a 1 at every power of 2 position, we have some pattern P at every 2 power of position. And the length of the pattern is going to be the size of the alphabet. So sigma is the alphabet here, and so this is just the size of the alphabet. So we're going to place some string at every power of 2 position, and its length is going to be the size of the alphabet. And we're going to use this crucial lemma, which will take up some proportion of Ben's talk. I don't know what percentage, but 65% of Ben's talk. which says that there exists some pattern P, so that if you slide it over all 2p length strings T, then it's going to generate lots and lots and lots of different possible outputs. Right? So if you remember, you have a short thing, you slide it over a long thing, and you get, in this case, p outputs. And you want to know how many different arrays of outputs could you get? The Hamming output arrays, you might call them, Hamming array outputs. And we could argue that there exists some pattern out there, so that when you slide along, and you vary what the thing you're sliding along is, like the stream you slide along, there are lots and lots of different possible outputs you can get. And in fact, lots and lots here is like sigma to the sigma. Yeah.
So this is for I'm confused by the quantifier.
Yes.
Because for each fixed length string T, there are only P different.
Right. So it's going to be we're going to have one of these, only one of those, and lots of longer things.
So there's sigma to the 2p.
Yeah.
So or sigma to the sigma. So you've got up to that theta, there aren't any more than that many strings.
It's the highest entropy we could hope for.
Yeah. Okay.
Yes. Great news. Exactly. So that's as good as you can get, up to the theta. Exactly right. So this thing exists, and it's non-trivial to show that it exists, but it does exist. So once you believe that exists, then we are in a really good shape. What we're going to do, remember this is our pattern, we're going to have this string, this is our string, let's call it, so it's going to have this pattern here, P, at every power of 2 length position, it's going to be of length sigma. Our stream is going to be made up of chunks of length 2 sigma, and because the problem is just having lots of different outputs is not quite good enough because there's a theta here. The entropy could still be low, unfortunately. So we need to sample these things from a subset of the possible strings of length strings of length 2 sigma, so that we always get, for any 2 strings, we get distinct outputs from P. So we need to take some sort of subsampling in order to make sure entropy is still high. So the general idea is we show the existence of one of these things, gives lots of different possible answers, and then we sample these so that we get a different answer for any 2 different strings in it. Okay. So that's the general proof idea. And if we can do that, then we show we recover a linear number of symbols from a window of length L. And so our entropy is going to be as follows. The unknown region of length L, we split it into chunks of length 2 sigma. Each one of the chunks of length 2 sigma has sigma to the sigma of different possibilities, so it gives us log of sigma entropy. And so we work it out, we get L times log sigma entropy from a region of length L, and log sigma is simply our definition of delta. That's more or less all I'm going to say about the Hamming distance problem. But does anyone have any questions about it before I... Yes?
You don't mean that this term about sigma to the sigma is trivial, but should be adequate?
Absolutely not trivial, and you should go to Ben's talk to find out how it works. I definitely don't mean it's trivial. It's very, I mean, I don't want to go on about too much, but it's very nice. It involves a bit of additive combinatorics and a lot of fun. Okay. So we get the same low bound, because all we need, remember, for our technique was to show that the entropy over L outputs was L times delta, we did before, and that gives us the same low bound as before. So we get delta over W times log n per symbol, amortized low bound. So we did inner product, we did convolution, we did inner product, we did multiplication. We've sort of talked briefly about Hamming distance. It's worth thinking, and I'll mention again later on, what happens with other distance functions? Well, a natural distance function you might imagine is simply L infinity distance, right? You have 2 vectors. What's the L infinity distance? The maximum absolute difference between symbols that are lined up. There's just an example. And you think, well, I'll just go ahead and do that as well. But the problem is, every time you come up with something new, there's a, well, is obvious to anyone, the technique just fails completely with n infinity. And the reason is because the whole method relies on the assumption that you can determine the value of the function in the unknown region by subtracting off the values from the known parts. Right? So if I have inner product between two vectors, and I tell you the inner product, for the parts on the left, the part on the right, and I tell you the inner product of the whole thing, you can tell me the inner product of the bit in the middle, just by subtraction. N infinity, if I tell you the n infinity, what am I going to do, right? Of the bit on the left and the right, it's impossible to, unfortunately, there's no equivalent of subtraction for the concept of n infinity. If I know the symbols on the left and the right and the bottom and the middle, I don't know the bit in the middle, I can't tell you, I tell you the n infinity of the whole thing, I can't tell you the n infinity of the bit in the middle. So as soon as you veer off the narrow path, you find there's something open and something that needs new ideas. N infinity is particularly tempting because we don't know anything better than a naive algorithm. Right? These methods, these problems I've described to you, we have clever methods of doing them. But for n infinity, all we know how to do is just n time per new symbol that comes in. And yet, currently, we have no lower bound at all.
So by L infinity, what exactly are you...
Every time a new symbol comes in, you have to do the L infinity between your fixed vector and the last n-length suffix of the stream.
I see. So you're viewing...
It's the maximum...
So if you say your numbers are 1 through n, your difference is the difference in the value of...
The absolute difference, yeah.
The absolute difference.
Yeah, it's the maximum absolute difference. Yeah.
Okay.
Yeah.
So you're thinking of them as numbers.
Yeah, exactly.
As opposed to...
I went back to numbers, yeah.
Okay.
I veer backwards and forwards between numbers and symbols. Yeah,
Okay.
that's true. Yeah. So that's very tempting, right? Something which has only a naive algorithm that we know of. You feel there should be some lower bound. Okay. Part 2. So what we've done so far has, the entropy has always had this delta in it. And when delta was the number of bits needed to represent a symbol. Now, again, with one sort of slightly practical hats on, if one believes theory is inspired by practice in some way, when do we have large alphabets? If I want to perform pattern matching on all the genomes in the universe, the alphabet relative to one genome, the alphabet size hasn't really increased. Right? If you want to search all text written in English, the alphabet size isn't any bigger than one text. So you might imagine that there are lots of practical situations where really the alphabet size is fixed, but the data gets larger. The alphabet size doesn't always grow with the data. I have more optimistic co-authors who have lots of lovely examples where the alphabet size does grow with the size of the data, but I think it's of central interest, really, to imagine a situation where the alphabet size just doesn't grow when the input size gets bigger. Unfortunately, if the alphabet size is small, let's say binary, then our conditional entropy is going to be low. The delta is going to be 1, right? And if our word size is large, because ultimately we'd like lower bounds in a realistic model of computation, where the word size is going to be like log n, so that we can address all the memory, then this is very bad. The entropy is going to be low compared with the word size, and we end up with something that doesn't give us the lower bound at all. Now we can just reduce the word size, you might say, and make the model slightly less realistic, but nonetheless. But then when we do that, we have to change the encoding argument. So I'll just tell you for a little bit now how you do that. It doesn't address the question that maybe we don't want to reduce the word size, but let's say we accepted that we were going to reduce the word size to cope with the small alphabet size. We still need to do some work to get things to function. Right. So we had our information transfer tree, if you remember it. And just to rewrite it slightly, we have that the entropy of the outputs, given all the fixed stuff is fixed, is at most W times some constant times log n times the expected information transfer. Now, where does this log n all of a sudden appeared from? Well, I'll tell you about it in a moment, but essentially, we need log n bits in order to represent an address. And if you remember, our encoding represented the address and the contents, and I didn't really mention to you that in fact one of those had to be at least log n, but it does. So this is our address space encoding. That was what we did before. So if you recall this picture here, this was the address of the information transfer, this was the contents, and in order to actually be able to represent these addresses, we're going to need at least log n bits. Previously I wrote that as W, but really W secretly had to be at least log n. Although the technique didn't work at all. Right. So this is the problem. Because we're going to have this delta that's going to be small, but we're going to have this log n in here as well, which is going to cause us some difficulty. And this was encoding based on addresses. Well, what we can do instead is come up with a different encoding. So an alternative encoding, rather than storing the addresses of all these cells, is to store the time at which they're read when you're doing this work here. And so this is a little picture of it. So for every cell in information transfer, we're going to store the read time, so it's the first time which it's read after the unknown period, and its contents. And this will require fewer bits if the read time is small, and more bits if the read time is large. But it's an alternative way of encoding the information transfer. Is that clear what's going on?
So how can you reconstruct from this information now?
Right, so our algorithm runs along here, jumps over, and it does a read, and it says to itself, what time am I doing my reading?
Oh, I see.
Is it one of these times?
I see.
Okay. Right. Okay, so we have two encodings. We have our address-based encoding, which you remember gives us this lower bound for the information transfer, which is W plus some constant times log n times the expected information transfer, is on the right-hand side, left-hand side is the entropy. And we have our counting-based method, which is going to give us this bound here. So this is just the number of different ways of choosing the cells from all the things that are read, because it's possible that in this region, after an unknown period, you might read lots of things that are not in the information transfer. Right? There's no reason why we only have to read stuff from the information transfer. And if we do read lots and lots of stuff that's not in the information transfer, then this number is going to be big. Right. And plus some other terms we need here. This just represents the contents, and there's some other little terms, basically. So you have these two different things. And what we want to do, of course, we want to balance them. So you want to give a combined encoding, because in some cases this is going to be good, and in some cases it's going to be bad. Right, so we want to balance these two things here. Oops, trouble with various security courses. Right. Well, and when we balance these two encodings and combine them with the lower bounds of the entropy which we previously gave in the previous hour, what we end up with is the expected information transfer is going to be at least delta times the LV here represents the size of the let's see, left or right subtree of this node, divided by W times this log, and the log just comes from minimization from the balancing of the two terms. That's where it comes from. Okay. And so this here looks all right. And maybe we can do something useful with that. Yeah. And we plug it all in, and we get the expected amortized cell probe lower bound is now going to be delta log n over W plus log n, which holds for any randomized algorithm. Okay. So if that delta equals 1 and W equals 1, so in other words, we're going to have the bit probe model, which I think was mentioned yesterday by Anna Gal. So we imagine that there are bits coming in, and our word size of size 1, and we get log over log for our lower bound. So which is better than we were able to achieve before. So the point of the story is by having this counting-based encoding, combining it with an address-based encoding, and balancing them as well as you possibly can, we're able to reduce the word size down to 1 and still get a meaningful lower bound on our problem.
So obviously you could have W equals log n and the bound would still hold.
Yes.
So you can, that's
Yes.
a little nicer
Yes.
than W equals 1.
Yes.
Delta equals, yes.
Yes. It's absolutely true. That's right, yeah. You're quite right.
Now, if you had log n bit words and weird operations, would you be able to solve these problems efficiently, like pack weird stuff into?
So that's a great question. And the answer is probably not, and the last half hour or hour of the talk will be about that. Yeah. But that's a major, in my mind, open problem. Yeah. But it's a great question. And it's my favorite question, in fact. Yes. Right. Okay, so that's the situation with the existing distant function we talked about, where we can then reduce, we can predict the full range of values of W and delta. Okay. Now, Hamming distance is an interesting problem to study, and convolution is an interesting problem to study. But of course, very fashionable these days is to study the problem of edit distance and also longest common subsequence. But the results talk about are going to be similar for both of them, but I just focused on edit distance. And again, we move from convolution and multiplication and Hamming distance to edit distance. Again, something funny happens, which shows, in some sense, the weaknesses of our techniques. Everybody knows that edit distance is at least as hard as Hamming distance. Right? Everybody knows that. Right? If I asked a poll, you'd all agree. Right? We have a log lower bound for Hamming distance, so surely we must be able to get a log lower bound for edit distance, you might say. But it's a bit awkward. So let's first of all define a problem and then say why it's awkward. So what we're going to do is we're going to define a version of edit distance that makes sense in a stream. So instead of having this sort of sliding window thing we've been talking about before, we're going to talk about the minimum edit distance between our fixed vector, which has changed letter, but anyway, it doesn't matter, our fixed vector here, or fixed string, and any suffix of the stream that's coming in. So we're going to minimize here over these h's, which are less than I, and this is just a suffix of the stream, of the edit distance between the fixed vector, fixed string, and any suffix. So a new symbol comes in, we want to give the minimum edit distance between our fixed string and any suffix of the stream that we have at the moment. Why is it difficult to prove a log lower bound for this problem? Is it immediately obvious to anyone? Consecutive outputs can only differ by 1. So the entropy of the outputs is small. And we crucially require the entropy of outputs to be large for our proof techniques. Right. Previously we argued in the Hamming distance case that for L outputs, the entropy of the outputs was like delta L, where delta was the size of the symbol. But in the edit distance case, the entropy of L outputs can only be like L. And this is fatal for our technique. So let's try and go over that a bit more and see what we can and what we can't do about it. So previously, remember, we were interested in showing that there was a lower bound for the entropy, conditional entropy of the outputs, which was like delta times L. Well, LV is the size of the subtree from the node V. And we could call nodes that have this property, we call them high entropy nodes. And we basically argued that almost all the nodes in an information tree were high entropy previously. Edit distance, unfortunately, can't have any high entropy nodes because of this feature that the consecutive outputs only differ by a constant, and therefore they can be encoded in a constant number of bits. So you can't possibly have entropy for the you can't possibly have conditional entropy that's higher than LV, in other words, right? The size of the subtree. Whereas what we want is something like delta LV, but it's not possible. So instead, we have to abandon for the moment, because we don't have the technique for it, our hope of producing a lower bound for large word sizes for the edit distance problem. and see if we can produce at least a lower bound in the bitprobe model. But of course what we'd like, open problem number whatever, is some way of proving a lower bound with large word sizes, which I just don't know how to do as yet. And to confirm all our suspicions that distance is at least as hard as Hamming distance. Right. We can at least find nodes that have medium entropy. And medium entropy here, which is much more modest than high entropy, we define as saying that the conditional entropy of the outputs is at least the size of the region below the node divided by something like square root of log n. This is obviously a much more modest claim, but it's something at least that we can show. And I'll show you how we show that in a moment. So what we're going to do instead is we're going to argue that most of the nodes have medium entropy in the information transfer tree, and we're going to use the bitprobe model in order to give our lower bound. So we need a hard distribution in order to do this. So our stream is going to look like this. Our stream is going to be made up of sections which are going to have row diamonds, and I'll tell you what row is in a bit, followed by a T or an H, and a T or H is just meant to be tails or heads of a tossed coin. So we're going to have tail or head, row diamonds, tail or head, row diamonds, tail or head, row diamonds, so on and so forth. Right? So the only randomness happens one every row steps, the rest of it's fixed. And this diamond is just some symbol. And our fixed string, which is now called F, the multi-changing naming string, is going to have H followed by row stars, and H followed by row stars, H followed by row stars, H followed by row stars. And these stars are just a symbol that doesn't occur in there. Diamond's a symbol that doesn't occur in here, star is a symbol that doesn't occur in there. And the general idea, which I may say in a moment, I'm not sure. I should have maybe said, sorry, these H's are at power of 2 positions. I forgot to mention that. These H's are going to be a power of 2 positions. That's what the dot's meant to symbolize. So the general idea is going to be that this padding with diamonds is going to force the edit distance to be very likely to be the same as the Hamming distance. This is generally what's going to happen. It's going to make basically insertion and deletions be a waste of time. You might as well just do substitutions. That's what's going on with this padding. So we have our fixed string, we have H's at power of 2 positions, and in our stream here we have head or tail, row diamonds, head or tail, row diamonds, head or tail, row diamonds. So that's the input distribution. Is it clear what the input distribution is? Is it unclear? Okay. Good. So why is this hard? Well, under this input distribution, we can show that that for Hamming distance, remember it's an edit distance problem, but for Hamming distance under this input distribution, we can show that the entropy of the outputs, given all the fixed stuff is fixed, is at least LV, which remember is just basically the size of the region, divided by rho. Okay, that's not too surprising. And then we can also show that for the edit distance problem, if rho is set to be something like square root of log times log log n, then there's a good probability the edit distance equals the Hamming distance. Because all these diamonds here make it worthless for you to do insertions and deletions most of the time. You might as well just substitute your head for a tail, or your tail for a head. So it's sort of a squeezing lemma of some sort. And in fact, this is also true. There's also in the paper, we show this is also true for the longest common subsequence problem, but I won't discuss that here. So given those two facts, we get that for the edit distance problem, the entropy of the outputs, given all the fixed stuff is fixed, is at least LV divided by rho, just as it was in the Hamming distance case, with some constants that change. And rho here is square root of log n log log n, because quite often it's just the same as the Hamming distance. So that's the general idea. And actually what's quite interesting is if you read, so we published this a few years ago, the sort of more modern papers on Seth lower bounds for edit distance, they have reductions that are similar in feel to this one which we have here. So there's obviously an idea that sort of generally caught on. So we can plug it into our machinery now, and we get that we get a lower bound overall of the square root of log n over log to the 3/2 in the bit probe model for edit distance. So there are two things to say about that. One is it's not log. Why not? Well, because our reduction wasn't good enough, and it should be, I believe, or at least log over log. So if anybody knows how to do that, that would be great. And secondly, just for a fun exercise, what's the smallest value of n for which that term there is bigger than 1? Anyone do it in their head? It's quite big. Quite big is the answer. So those on more practical bent who take a look at these low bounds do sometimes giggle. But nonetheless, the top is exponentially larger than the bottom, I claim.
It's the omegas.
Exactly.
That's killing.
That's exactly right. Yes. Well, I claim, this is exponentially larger than that, but plug in 2 to the 128, you'll find it's still less than 1. But nonetheless, it's a small detail. It's a small detail. But so I think it's a nice, really it's frustrating. Edit distance should be harder than Hamming distance, so very nice if we could find a way to get the lower bound for edit distance to be at least as high as the lower bound for Hamming distance. But I don't know how to do it. Okay, so in the binary case, Hamming distance is basically the same as convolution, so we can certainly solve that in n log n time offline, and therefore log squared time per new symbol online. Right. Edit distance, on the other hand, in the RAM model, it would appear to take linear time per new symbol that comes in. Right. But you imagine this dynamic programming matrix, you get a new column, takes linear time per new symbol. So this lower bound really seems a long way away from the upper bound. However, in the self-probe model, it's not so far. And I find this sort of independently interesting, and particularly in the context, I find it interesting in these Seth lower bounds and people interested in the hardness of edit distance, that there is, from my view, it's very surprising to me what the self-probe complexity is of streaming edit distance. Right. In the RAM model, it just appears to be linear. I don't even know if you can save log factors in the streaming setting. But in the self-probe model, it's not the case. So I'm going to show you a self-probe algorithm that takes log squared n divided by w cell probes per arriving symbol to give a new edit distance. It's going to be amortized. It has some oddities, which I may go into a little bit. I don't know how much. One is that the algorithm depends on the pattern. It's non-uniform in a dramatic sense. You get a different algorithm basically per pattern. Or you can imagine we just did some exponential time pre-processing of the pattern, all of which is completely kosher in the self-probe model, but is slightly odd, you might say. But our low bounds hold no matter what. But in some sense, we haven't excluded the possibility that there's a lower bound of higher than log squared, despite having given upper bound of log squared, because of this slightly oddity here where we require this exponential time pre-processing, which of course is free in the self-probe model. And also algorithms amortized, maybe there's a better worst case lower bound. Anyway, this is something to discuss maybe another time. Right, so let's have a go. Let's remind ourselves about edit distance. So edit distance, we have this dynamic programming table. Our pattern goes down here, and our stream goes along here. Each cell is going to be some node. We're going to look at it in a graph sense, but anyway, we're going to say that, well, let me just actually, it might be easier if I just give you very quickly a sort of the classical recurrence. The classic recurrence says that for this problem, all these values along here are going to be 0 because of our streaming setting, and the value of a particular cell depends on the one above, the one to the left, the one up and left. So it's the minimum of the one above, the one to the left, and the one up and left plus 1 if the two symbols are different from each other, this one and that one, plus 0 otherwise. Okay. Right. So we can see this, we can look at this as a graph problem, so it's a shortest path problem, and we're interested in the shortest path from the top left here. If we wanted this to the bottom right, this would give us the edit distance when this symbol comes in. So every time a new symbol comes in, we want to find the shortest path from the top left to some cell on the bottom row here. Right? That's what the distance problem is. That's what we want to do. Okay. So that's sort of a classic problem here. And you might imagine that the reason why it takes, in the RAM model, something like n squared time is because of the dependency, right? Each cell depends on the one above, the one up and left, the one on the left, and in some sense, you can't do anything about this dependency. But that turns out to be not the right intuition. Right. So, where have we got to? Between the top left and the bottom right, there of course could be multiple shortest paths. That's something important to understand. This isn't just necessarily one unique one. And so let's try and work out the algorithm. Let's try the algorithm. Right. So even in the CellPro model, if we wanted to compute all the values in a column, which one might think would need in the future in order to do these sorts of paths, it's going to take us n time. So what our algorithm is going to do, it does a number of tricks, and one of which is it doesn't compute all the values in a column. And in fact, even the values it does compute, they're not all correct. But exactly the right ones are correct. And the ones that aren't correct won't ever be needed. Right. And even that's not enough, but we'll get onto that in a moment. Right. So we're only going to compute some of the values in our algorithm in every column. Everything above a certain value we'll just put to, above position we'll just put to infinite. Right? And then we're going to give some finite values to the things below a certain level in a column. So there's going to be a bunch of computer stuff and a bit of non-computer stuff. Okay. Now, the edit distance, remember, is the shortest path. And if the shortest path went via something which we put infinite for, this would be very bad, right? We'd have, because remember, this is a whole lot of dependencies. We follow kind of a chain backwards. So we really wouldn't like that at all. That would be a disaster. So we have to make sure that the amount of stuff we compute is high enough so the shortest path doesn't, or at least one of the shortest paths, doesn't go through it. That's the first thing we have to make sure. Secondly, actually we can't even afford to store that. So what we're going to do is we're going to store these columns in a compressed format. Now, if one thinks about the dynamic programming table, consecutive values in a column either stay the same, go up by one, or go down by one. And our method of compression, which I may talk about in a bit more, is really very straightforward. We compress sequences of values that go down by one just by saying their start and end position, and everything else just gets stored normally. So we have these blocks. Maybe I can write down a block, right? So 32, 33, 34, 35, 35, 34, right? 35, 36. Right. And each one of these blocks gets represented by a constant number of words. And if it stays the same or goes down, it makes a new block. So this is increasing, 32, 35. So we can just say it starts 32, ends at 35. That stays the same, so we've got to start a new block, just got 35 in it. That goes down, so start a new block. This goes from 34 to 36. So we just say it starts 34, ends at 36.
I see. So it's I thought, so increasing sequences
yeah.
are unlike.
Exactly, yes.
Okay.
Yeah.
I thought you said decreasing.
Yeah, well, yeah. Yes, depends if you're going, exactly. Depends if you're looking down or up, yes. Yes.
Oh.
Yeah. I'm a bit lazy about whether I'm looking down or up, it's true, yes. Okay. So, right. So, where have we got to?
And then you got to search in that.
Yeah, but time is.
You've got an index, you got to find it somehow. Maybe not.
No, we don't. Yeah, we don't need to do that. Yeah. Also, remember, computation is free. So, yeah, don't forget that. It's a very important thing to remember, right? So here's a little picture which Ben very kindly drew for me, just so we can be clear what's going on. So we look at this region here, for example. It has some values in it, and we have these different blocks. So each one of these blocks is going to be represented by a constant number of words. Yes. Say it again, sorry.
I was wondering which one you choose to compute.
I haven't said, but it's a great question. Thank you very much. How do I choose how high the column should be? I think that's the question. How do we choose? Right, but I haven't said yet. Okay. So, where have we got to? Right, we want to compute this value down here. What we're going to do is we're going to actually compute these values here, and we're not going to compute any of these values here. So, right. Now, there's an important trade-off here, which I think is one has to understand. Because we need to output all these cells going along in the future. And if we don't, in order to output these cells in the future, we'll need cells in the past, right? So if we don't compute much stuff, it's going to make it very difficult for cells in the future. And if we get a lot of stuff, then it's going to take a lot of time to do it. But it'll make it easier for stuff in the future. So there's a trade-off there, and there's a sort of collection of trade-offs, but it's one of them. So anyway, in order to compute these answers here, what we're going to do is we're going to identify some column, which we call row I, so it's a function of I, which I'll tell you explicitly what that function is in a bit, which is sometime in the past, I better not stand there, which is sometime in the past, and we're going to look at the values in the past here, and try and use the values which we have in this column in the past in order to give these things here. Unfortunately, if we chose this column, it would be a disaster, because it turns out that the lowest shortest path goes via something above the computed values, and so we can't get the right answer. And we know some various things, right? We know there are some various facts we know. One fact we know is that if you want to compute all these values here, the shortest paths can't possibly go via here. This is because basically it costs us to go down. Right? It always costs us 1 to go down. So we have to get down to here somehow, and it's going to cost us too much. So we know something already about which cells the shortest path can possibly go via. These are the ones are all excluded. So instead we choose some column which is a bit closer and a bit higher, and hits this point here, and we hope that we've already managed to compute all the information in here. And if we have, then we can use this column in order to tell us the answers here. So how long is that going to take us? Well, here we use the magic of the cell probe model. The magic of the cell probe model says that if we have this column here, then all we need to do is read in this column here, read in the stream of here, and we immediately get the answers for here. Right? This is the magic of the cell probe thing. Something that should have taken quadratic time is now taking us linear time. We need the size of the perimeter, basically, of the rectangle, not the area of the rectangle, in order to do it. So this is important to understand. This is where the magic of the cell probe model is coming in. We just need to read this in, read that in, and then we get this immediately. So how big should these things be? Well, remember this is a position row I, so this width here is going to be I minus row I. And the trick we're going to do is we're going to balance this so that the height of this column, when compressed, is going to be of size proportional to I minus row I as well. So the number of blocks, as I've called them, in this column here is going to be like this size as well. So what we need to do is, the amount of work we do is the sum of this distance and this distance. Because in order to read in, we don't actually worry about the real height of it, we only need to worry about the height of it in its compressed formulation. Yeah.
So you'd have to know something about the full prefix in order to know how high and compressed things go.
Well, it's always, so, right, so this, I mean, it's actually a constant. So this is 8, in fact, this number here. So we need to only read it into 8 blocks in order to read this in. Yeah, and this is actually, 8 times this thing. Yeah, 8 times, there's a constant 8 there. And there's a constant 3 here, but anyway. This is actually going to be 3 times I minus rho I, and that's actually 8 times I minus rho I. And those constants simply come from the angle of this line.
What's the angle of that's 8/3?
No, this angular line is, I think you go 1 across and 2 up.
Oh, I see.
I think so, yeah. But there's the extra.
Oh, and then ceilings and floors.
No, there's an extra complication as well, which is a subtlety here, which is that even though this can be represented in 3 times I minus rho I blocks, that doesn't tell you anything about how the same height along, how many blocks there are in this part here. But if this was a lot of blocks, then the shortest path couldn't go. The shortest path couldn't go through it, basically, because that would mean that the edit distance was very large. So there's just an extra subtlety there. Yeah. So it's 8 rather than 5 or something. Yeah. Yes. But yeah, there's a constant chat. Yes. But that's the general idea. That's the specific idea, in fact, that these things are encoded into blocks. So some version of run-length encoding, what do you want to call it? And these encode into blocks. This thing needs to be higher than this thing. Right. And we look it up, we read the blocks, the first 8 times I minus rho I blocks, and we do a computation, and it tells us these.
Then you're going back in.
So there's a nice picture, which Ben sometimes draws, which I'll try and draw, but I'll do it in a moment. Actually, I want to tell you what rho, well, maybe I'll tell you what rho I is in a second. Okay. Right. So we have to set rho I to something. The smaller rho I is, the further back this way we go, the higher the column has to be. And that more work we'd have to have done in the past in order to compute it. But the smaller rho is, the more we exploit the self-pro model, because more the difference there is between the perimeter and the area. Right. So you want to find a rho I that balances these two things between each other. And it turns out that this is a good function. Rho I is just I with the least significant bit set to 0. Okay. So there's a nice picture, which I hope I draw as well as Ben draws it, which...
least significant 1 set to
yes, the least significant set bit set to 0. Yeah, right. So the nice picture which... Well. Right. So each one of these things relies on something in the past, right? So that relies on that thing there, this relies on that thing there, that relies on that thing there. It's right. So the point is that it's like a skyline, basically. These columns all rely on something in the past, and this strange function here effectively makes the heights of the columns to be as I've drawn there. That's the idea of it. So if you do this, then you'll find that, well, various things. One of which is that this nice fact here, which is that we sum I minus rho I from n to 2n, let's say, then we get n over log n, which is nice, right? Which means that our overall time complexity is now going to be n log squared over w, which is rather pleasing. That's really the algorithm. So, of course, someone might say to you, well, can you actually make a better RAM algorithm out of that? It seems tricky. And I don't really know whether what we're learning here is something about the self-pro model being too powerful, or whether we're learning something deep about the edit distance. But it's certainly not the case that the reason why distance is hard is fundamentally because of dependencies within a dynamic programming table. Because the dependencies exist here as well, and yet we can exploit the power of free computation in order to dramatically speed up the edit distance computation in the stream. So I find this surprising and rather pleasing, but anybody has any more thoughts about it, I'd love to, about consequences or things one can do with it, I'd love to talk about it. Now I've completely lost the clock. How are we doing for time? Oh, okay. So let's stop and take a break. Thanks. Okay. So we finished on this note here, where we talked about lower bounds, Hamming distance, and convolution. For edit distance, I didn't mention longest common subsequence, but with the same lower bound applies. This is a windowed version of it, where you want the longest common subsequence between your fixed string and the latest n-length window. And we have the upper bound for edit distance. Of course, in terms of open problems, I guess what people are most interested in, there are quite a lot of them. In particular, although we have the same lower bound for longest common subsequence, we don't have the same upper bound. We only know an upper bound of square root of n, which I don't think we even put in the paper because we felt it wasn't exponentially good enough. And the windowed version of edit distance, I don't think we got anything for that. So lots of related problems for which we don't know the answer. But the key question for me is how to show that edit distance is at least as hard as Hamming distance, which we also haven't succeeded in doing.